On the 11th of March 2011, Japan didn't just endure the deadliest disaster of its modern era. It collided with a geological warning that scientists are only now beginning to fully understand. At 2:46 p.m., the seafloor off the Tohoku coast ruptured with a force no model had truly prepared for, unleashing a magnitude 9 megaquake, the most powerful ever recorded in Japan. Within minutes, the ocean rose into towering tsunamis, reaching heights reported near 30 meters in the worst-hit areas, sweeping inland with such speed that entire neighborhoods were erased before evacuation routes could even function. More than 18,000 people were killed, and at Fukushima Daiichi, a plant engineered to survive extreme events fell into meltdown after the tsunami triggered a catastrophic loss of power, turning a natural disaster into a technological crisis that stunned the world. But what the cameras captured, the black water, the debris fields, the explosions, was only the surface layer of what truly happened. Beneath the Pacific, the Tohoku rupture behaved less like a single earthquake and more like a system snapping in ways scientists once considered improbable. A cascading failure across the plate boundary that released energy on a planetary scale, shifting parts of Japan by feet and subtly nudging Earth's geometry. For years, the disaster was framed as a once-in-a-lifetime tragedy, an isolated catastrophe that Japan would rebuild from with time. Yet the deeper the data goes through seafloor measurements, reprocessed seismic records, and drilling evidence pulled from the rupture zone, the more unsettling the picture becomes. Tohoku may not have been an ending, but a beginning. The stress released on that day did not simply vanish. It redistributed, migrating through the Pacific Ring of Fire like a pressure wave through a living system, forcing experts to confront a question that feels almost impossible to say out loud. Was March 11 a singular nightmare, or the first domino in a chain reaction that could threaten fault systems around the entire Pacific Rim? Under normal conditions, Japan's seismic defenses are built around rules scientists trust. The country sits atop one of the most violent plate boundaries on Earth, where the Pacific Plate is forced beneath Japan along the Japan Trench, storing energy for centuries before releasing it in rare but massive ruptures. These events are expected to follow patterns. Stress accumulates, a fault breaks, energy is released, and the system resets. Japan engineered its warning systems, seawalls, and evacuation planning around those assumptions, refining them through decades of earthquakes and historical records. On the 11th of March 2011, those rules appeared to hold at first. The Japan Meteorological Agency's early warning system detected the initial tremors within seconds and issued tsunami forecasts based on models calibrated to past disasters, predicting waves of roughly 3 meters. Coastal defenses, many standing 10 meters high, were designed precisely for that scale of threat. But the Earth did not follow the script. The rupture expanded faster and farther than the algorithms could resolve in real time, and the true scale of seafloor displacement remained invisible during the critical first minutes. In towns along the Tohoku coast, the gap between the first siren and the arriving water shrank to mere minutes, sometimes less, while power failures and damaged relay towers fractured the warning network just as it was needed most. The failure was not technological incompetence. It was a collision between human prediction and geological reality. The models assumed the shallowest parts of the fault near the trench would slip less, dampened by weak sediments, limiting tsunami height. Instead, those shallow zones would later prove to be the most violent contributors. Japan did everything the rulebook demanded: advanced sensors, strict building codes, massive concrete barriers, yet the disaster exposed a devastating truth. When the underlying assumptions are wrong, even the most sophisticated defenses become illusions. What broke on March 11 was not only the fault beneath the Pacific, but the belief that megathrust earthquakes could be reliably constrained by past behavior, and that realization would force scientists to confront data they never expected to see. What shattered that belief was the data that followed, numbers and measurements that simply did not belong in any existing model. As researchers reconstructed the rupture using finite fault inversions, seafloor GPS acoustic sensors, and reprocessed seismic waveforms, a disturbing picture emerged. The Tohoku earthquake did not rupture a single fault segment. It tore open a chain of segments in rapid succession, spreading across nearly 500 kilometers of the plate boundary in minutes. Instead of stopping after releasing stress in one zone, the rupture accelerated, racing along the fault at speeds approaching 7 kilometers per second, faster than most earthquakes ever observed. Even more shocking was where the largest motion occurred. Conventional theory assumed that the shallowest part of the fault, closest to the ocean trench, would slip the least, cushioned by loose sediments that should absorb energy. The data showed the opposite. In several offshore regions, the seafloor lurched by as much as 50 meters, an almost unimaginable displacement that directly generated the colossal tsunami. This was not gradual creep or localized failure. It was a seamless cascade, a system-wide release that ignored decades of seismic assumptions. The mystery deepened when Japan launched the J-Fast deep-sea drilling project, sending a research vessel to penetrate nearly 7 kilometers beneath the Pacific and sample the fault zone itself. What came back up stunned the scientific community. Core samples revealed a thin, gray layer of finely ground clay, less than a few meters thick, sitting precisely along the rupture plane. Laboratory tests showed this clay had an extraordinarily low friction coefficient, around 0.08, meaning the fault behaved less like grinding rock and more like a lubricated surface. Temperature sensors lowered into the borehole added another layer of alarm. During the rupture, frictional heating had driven temperatures toward hundreds of degrees Celsius, triggering thermal pressurization that forced water out of the minerals, spiking pore pressure and reducing resistance even further. In simple terms, the fault briefly became almost frictionless, allowing the Pacific plate to slide beneath Japan with catastrophic ease. This was the terrifying truth hidden beneath the tsunami waves. The scale of the disaster was not just about accumulated stress, but about the unexpected physics and chemistry of the fault itself. Tohoku did not just break the ground, it broke the assumptions that guided tsunami risk and megaquake forecasting around the world. The consequences of that hidden mechanism unfolded not only in rock and water, but in human lives, caught directly in its path. Along the Tohoku coast, the difference between survival and loss was often measured in seconds. Many residents heard the first warning, but had no time to reach higher ground before evacuation routes vanished under incoming water. Others never heard a warning at all as power failed. Sirens were drowned out by the roar of the quake, or relay towers collapsed. Elderly communities, fishing villages built just meters above sea level, and hospitals operating on emergency power were exposed to a disaster moving faster than any plan had anticipated. As the tsunami pushed inland, it overwhelmed seawalls designed for past extremes, ripping apart reinforced concrete, flipping ships into streets, and scattering entire towns into debris fields. Critical infrastructure failed almost simultaneously. Power substations flooded, water pumps shut down, and communication networks went dark across large sections of northeastern Japan. Rail lines and highways, engineered to flex during earthquakes, buckled under landslides and liquefied ground, while ports meant to serve as evacuation hubs filled with wreckage. Even the Shinkansen, a symbol of Japan's technological reliability, was paralyzed as service across the region ground to a halt. At Fukushima Daiichi, the tsunami triggered a total loss of electrical power, known as a station blackout, setting off a cascading failure that operators could no longer control. Cooling systems stopped, reactor cores overheated, and hydrogen explosions followed, transforming a natural catastrophe into a nuclear emergency that would displace hundreds of thousands and contaminate land and sea for decades. The aftermath did not fade with the receding water. More than 200,000 people were forced into temporary housing, their lives suspended in prefabricated shelters long after the headlines moved on. Health surveys in the hardest-hit prefectures revealed sharp rises in depression, anxiety, and post-traumatic stress, while suicide rates climbed well above national averages in the years that followed. Economically, the costs soared into the hundreds of billions of dollars, draining public resources and reshaping national priorities. The true damage of March 11 was not confined to the moment of impact. It spread outward through communities, institutions, and generations, revealing that when a mega disaster strikes at planetary scale, the human toll continues long after the ground stops shaking. As the physical destruction gave way to recovery, a quieter and more unsettling battle began to unfold over information itself. In the immediate aftermath, official statements emphasized control and reassurance, while internal assessments struggled to keep pace with the scale of what had occurred. Early tsunami forecasts and public briefings, based on incomplete data, had already underestimated the danger, and that gap between reality and messaging would haunt the response for years. At Fukushima Daiichi, leaked reactor logs and later testimony revealed that engineers recognized the severity of the meltdown far earlier than the public was told, but uncertainty, fear of panic, and institutional hesitation delayed full disclosure. Decisions were made behind closed doors about venting radioactive steam, expanding exclusion zones, and managing contaminated water, even as residents and local officials remained largely in the dark. This tension between transparency and control extended beyond the nuclear crisis. Seismic data from across the Pacific began showing unusual patterns in the years following the Tohoku rupture, with clusters of magnitude 6 and above earthquakes appearing in regions once considered relatively stable. Some analysts warned that the event had altered stress fields along the Pacific Ring of Fire, while others urged caution, arguing that correlation did not prove causation. Governments and scientific agencies faced a dilemma: acknowledge the possibility of broader implications and risk public alarm, or frame the disaster as an extraordinary but isolated event and preserve confidence in existing systems. Media narratives amplified the conflict, with stark images of devastation clashing against technical reassurances that few outside expert circles could fully interpret. For survivors, the uncertainty bred mistrust, as shifting explanations and delayed admissions eroded faith in institutions meant to protect them. The disaster exposed a hard truth that extended beyond geology. In moments of extreme uncertainty, information becomes as fragile as infrastructure, and the way it is managed can shape the long-term impact of a catastrophe as powerfully as the physical forces that caused it. The legacy of March 11 did not end with reconstruction or policy reform. It forced a fundamental shift in how the world understands megaquakes and the risks they carry. The Tohoku disaster revealed that the most devastating earthquakes are not defined solely by accumulated tectonic stress, but by hidden fault properties, capable of turning stored energy into runaway motion. Subduction zones, once thought to be partially self-limiting, were suddenly reclassified as systems capable of near-frictionless failure, able to generate tsunamis far larger and faster than warning models had assumed. For scientists, this realization redrew global hazard maps overnight, compelling reassessments of vulnerable regions from the Nankai Trough near Tokyo to the Cascadia subduction zone off North America's west coast. The lesson was stark. Past behavior is no guarantee of future limits. Stress can migrate, chemistry can change outcomes, and rare conditions buried deep beneath the seafloor can decide the fate of entire coastlines. For governments and emergency planners, the implications were equally unsettling. Evacuation windows measured in minutes are not enough when rupture physics defy expectations, and defenses built to historical extremes may fail catastrophically against unprecedented ones. For societies living along the Pacific Rim, the warning embedded in Tohoku is both scientific and moral. The question is no longer whether another megaquake will strike, but whether humanity is willing to confront uncomfortable truths before it does. Japan's 2011 catastrophe was not just a tragedy frozen in time. It was a message written into the earth itself, reminding us that the planet's most violent systems do not announce their intentions, and that ignoring what lies beneath the surface may be the greatest risk of all.